Зараз слово Герті Горті до Москви. So far, one of the requested four market promotes, and this one was positively position that week. So they have a class of right. Because I'm taking 5%.
mind. So I'm going to introduce Lilith, but before that, a kind of introduction or preview of. So I'm going to follow this textbook. It basically tracks what. Let's take it. Yeah, so that's an electronic textbook that I sent you the file. Were you able to open it? Yeah. So we're basically going to follow that. So, let's see how far we get today. Hopefully we can get through most of this concept of limit. I think I asked you that if we can see this before, heard of that. Yeah, I remember, I think, some of the formulas. I don't remember much. This is not charging. Okay. So, let's start with a preview of calculus. So, the idea of why do we have calculus? What is it for? And essentially, imagine you were driving from here to somewhere. Let's say from Yonge to where do you Jinji. Yeah. Okay. So you're driving from here to Jinji, and Okay, now for the next one. Alright. So you're driving from here to Chinchi, and so as you drive, of course you drive faster, slower, when there's a truck in front, you slow down. And when you finally get there, how long does it take? Possibly an hour. And if you know how long? 50? Yeah. So you went 50 kilometers in an hour. So if I asked you how fast did you go, you could say, well, on average, it took me an hour to go 50 kilometers. So 50 kilometers divided by an hour, that's 50 kilometers an hour. So that's your average speed over the whole journey. But you know that you weren't going exactly 50 the whole way. Yeah. Sometimes you're going faster, sometimes you're going slower. And now you could draw that. Are you in calculus also? You have calculus also? Yeah. Excellent. Tell me what? Oh, we love it. Do you know I've never made a lesson. This is one. So this is not going to So you're driving from here to Chinchi, and we can say your average speed is 50 kilometers an hour. Is that up to you? How fast were you going after at 23 kilometers? And you were at that point, how fast were you going? At this point in the journey. So I didn't really so this is supposed to be connected into that. Then there's a charger. Let me connect it to this one. Let me try it. No. So, here's the long way, and here is Chin-Chin. So you drove from here to there. You said this is 50 kilometers, and it took you 1 hour. Now, when you drove, so I'm going to draw a box. A little bit different. We call this time, and this distance. So here is numbers 0, and this is 0 time, and here is 1 hour. So really what we've done is we're taking this distance, and now we're putting it along here. Right? Yeah, so the long way would be here, Jimmy would be there. At time 0, you are where? You're here. And at 1 hour, where are you? You're at about here, and back here. Now, as you're going along, maybe you start off, when you leave the city, it's a bit slow, lots of traffic or something. So you're not moving very quickly. You all know how to get food from the So, the first 20 minutes is a good place. So there's 20 minutes, there's 40 minutes, we'll do it halfway, there's 50, 40, and, alright. So we might say, well, the first 20 minutes, we only went 10 kilometers. Right? It was pretty slow. So 10 kilometers, and then I need to 1, 2, 3, 10, 20, 30, 50. So after 20 minutes, we're only at 10 kilometers. But then you start being able to go faster. So let's say at 40 minutes, you were at 30 kilometers. That's huge. And then at 50 minutes, you could go really fast. You got almost all the way. But then there was an accident and it was very slow. And then you left. So then we might say, okay, maybe my speed, my journey will look something like that. Not a straight line. And now I ask the question. So go back to the question we had earlier. We said, well, the overall speed, the average speed, which is shown as v to c, the velocity, and the bar on top means average. So the average we said was the total distance, v, over the time, t, which was kilometers, an hour, which is 50 kilometers an hour. So that would be, if I started here, the total distance is where you ended minus where you started, 50 minus 50. And when you ended was an hour, when you started was 0, so the difference is an hour. We get that. And so your average speed was this straight line. But obviously you didn't exactly go all the way. So we want to know how fast were you going, let's say, at this point. How would you determine how fast you were going based on this curve? So the red curve tells us where you were at every moment in time. Right? So I put like a tracker on the car, and at every second, it tells me where your car is between here and Chin-Chin. So if you're asking where were you at 30 minutes, I go, well, 30 minutes. I was at about 22 kilometers. That's where you were. You can ask me anytime, I can tell you where you were. But now I want to know how fast were you going at 30 minutes. You were slow. And we know how to do average speed. I take a point here, and I take a point at the other end. So if I said, how fast will you go on average? Between 20 and 40 minutes. You can also ask that question. So we say the average speed of 20 is actually a change in position. So the change in x. I said d above, but this is more general. We have a change in position. I guess I put d, so let me use d. The change in d over the change in time. So what is the change in d in this case? So we need to know 40 minutes, where were we? We were 20 minutes, we were. So what is the change in d? From to what? Yep. Right. It only takes a few minutes to do. That's it. So remember, 30 minus 10, 20 kilometers. And the difference in time is what? Between 20 minutes and 30 minutes. 20 minutes. So 20 kilometers over 20 minutes. So what was my average speed though? Another way, if you want to put it in kilometers per hour, which is what we usually do, then you convert 20 minutes into hours. How many hours is 20 minutes? How many hours is 20 minutes? That's not 4.
How many maybe good?
Well, that's good. This is equal to 2.
Okay.
How many minutes in an hour? 60 minutes. So 20 minutes or 60 minutes is what fraction?
You said it's
What's the
no.
position?
20 minutes. So we want to know how many hours to be spent. 20 minutes is what fraction? Half an hour is how many?
This is
Yes. So 20 minutes is what fraction? So 30 minutes would be a half. How many? How about 15 minutes? Is what fraction of that? Quarter. Another question. How many? 50 minutes is a quarter, 30 minutes is a half. What is 20? A third is an hour. So a third of an hour. So 20 kilometers is a distance traveled in a third of an hour. What is the speed? To know the speed, you take how far you traveled divided by the time it took to travel. So if the distance in this case was 20 kilometers, and you traveled it in a third of an hour, so 20 divided by 1/3. What is that? Use it that way. In this course, you do not need calculators. Most of calculus doesn't involve numbers. It involves symbols. Calculators
put like percent or something. So, that's when you divide by something.
So you did 20 divided by 3. But you're not divided by 2, you're divided by 1/3. No, you multiply by 2. You divide by 3.
Yeah.
What does it mean to divide by a third? When you divide by a fraction,
Yeah, it's crazy. Oh, wait, yeah. No.
so if
Let's take a minute for now.
Hey, very good. So you remember, if you're dividing by a fraction, you're actually, you multiply by the inverse of the fraction. The 60. So you're going faster in this stretch. So, this should be good enough now. Should we try to do this here? So, we have 20 kilometers divided by 20 minutes, which is 20 kilometers divided by a third of an hour, which is the same as 20 kilometers multiplied by 3. Which is, sorry, 3 further. And so we get 65. So on this stretch here, the speed was higher. This was 60 kilometers an hour, whereas the green is 50 kilometers an hour. Now we could do another one. If I go here, that speed is probably going to be even higher. It's even steep. I increased my distance from this rise. So we call this the rise. So this should all be familiar from doing the equation of the line. Y equals mx plus b. So this is the end part, the slope. How, in the slope, you remember the equation of the slope? It's the slope of the line. When you have, so, y is m plus b. If I give you 2 points, 1 and 2, so point 1 is x1 and 2 is what is we're looking, we can draw a line between them. And we want to know the equation of this line. What is the slope of the line? So this you should be learning from the previous course. This is an interactive class. Yeah. Something like that. Something minus something. Okay. So now the question is, what is the something with something and something and something? So we have something. Okay. So you have something. The question is, what goes in each of those? We have 4 numbers. We have x1, y1, x2, and y2. Which one goes where? what do you think? X1 minus Y2. X1 minus Y2. So, to remind ourselves, right, this is X1. This is Y1. This is X2. This is Y2. So, this is Y. Y2 minus Y1. What does this tell us? What is Y2 minus Y1? Well, it's basically this which we call the rise. This is how far my line goes up, how much it rises along our axis. This, remember, how far it goes up. This is called the run. How far does it run along the x-axis, and how far does it rise along the y-axis? So rise over, this is the slope. Run. How high will it go over what distance? So now we could say, when you're walking up the road, and the road feels steep, that's because it's going, I went to Mount Bunda a few years ago. Now, that is very steep, isn't it? Yeah, that's very steep compared to. So what do we mean by steep? The slope is very high. At high meaning I have to go up in a very short distance, right? As opposed to here, if I walk up the ramp goes up 10 centimeters in 3 meters. So it has a short rise and a long run. I can slowly take time to go up that little distance. So it feels very gentle. But if I have a short distance and I have to go up a lot, then that becomes steep. So the higher the rise, the bigger the slope, the steeper it is. And the lower the rise, the lower the slope, the less steep it is. And then the run is the opposite. The longer, if I have a fixed line, I have to go up 1 meter. 1 meter is from the ground to here, let's say. If I have to do this in 10 centimeters, that's very steep. Not a lot of space to go up 1 meter. But if I say you have to go up 1 meter, but you have to go up a kilometer. In 1 kilometer, you have to go up 1 meter. I might not even feel it. So the run, the longer the run, the more gentle the slope. So it's like taking this P2, that's the run, I can just push it, I can push it back to here. Now my run will be this much. Now my run will be this, but my rise is the same. And here, the line is the slope. If I bring the point to here, now I have a steeper line, and my run is only this much. You can see how both the run and the rise have an impact on the slope of my line. So, all of this is saying, when we are asking what is the average speed, we are asking what is the slope. When the graph is distance versus time, the slope is steep. And so you can do this. You can say, okay, ask me anything. At this time for this side, I can look on my graph and I can say, okay, at this time you were here. So the run is time, which is in the denominator. This part. So this part here, this is the denominator. That's the run. So in our graph here, it's the time. And the rise is the distance time, which is the mean. So you can do this for any, but you're always getting basically the average speed. I just tell you point A, point B, how fast will you go in this speed. But then I can say, well, okay, that's nice. You can tell me that on this segment here, you were faster, your average speed. But look, what about from here to here? What about this one? Oh, that's even faster. What about right there? Well, that was even faster. At every point, my speed is changing. The car isn't going at constant 60 and then suddenly, now it changes to 80. Now it changes smoothly. So, this was the kind of question that people were asking. If I had, and it could be a graph of all kinds of things, it doesn't have to be position, but I want to be able to know how fast you're going at any time, in that moment, in that second. You say, oh, well, I don't know how to do that by doing this. I can get close. So what I could do is say, well, okay. Let's blow up our here, and let's say we have, this is your position. And I want to know how fast were you going, let's say here. This exact time here. We'll call this, what should we call it? So I want to know how fast, what is B at X? That's the question. So, from what we already said, you could say, well, I'm not sure, but I know from here to here, I could tell you were going this way. That's kind of close. Well, okay, I can make it from here to here. And then this much. And then I can zoom in and say, well, actually from here to here, you have new one. And you can keep making that interval smaller and smaller. And you're going to get closer and closer to the right answer. But it's a little average. If it were very small, you can make it very small, but it's still not at that point. So what we want to know is, at exactly the point X, what is, and we call it the instantaneous speed. So earlier we were talking about the average speed. This is now the instantaneous speed. Again, this is just one example, but this is what calculated is about. How do I find the slope at that point? And it's a process of, well, I can take these lines and I can make these approximations. So I'm approximating the instantaneous velocity. By finding, these are all the blue ones, they're all average velocities. It's always from this point to this point. And the 2 points can get closer and closer, but it's always from here to here. In between, anything can happen. Right? If you look very close in between the 2 points you showed, that maybe the red line goes like this. You've done something great there. So I want to know at X exactly how far am I going. So this is what calculus is for. And we're going to learn how to answer this kind of question. And essentially, the process of finding, the way you find the speed at that point, is to take these approximations and you say, if I could make it infinitely small, so this run, right, this average, if I could make the average like almost zero, then that should give me the speed at that point. So I want to take a limit. I want to say, if if I went closer and closer and closer, infinitely closer, what would be the answer? And that's what I want. So how do we do that? Then there's another kind of question that people have asked. And this one isn't, but there are other kinds of questions where what we want to know is the area under the curve up to some point. Given this curve, this red curve, which could be, well, it's a function. So that's what we want, a function. I know you want to say something. I said you remember the function. So this red line is some function of x. And there are different problems. So one kind of problem is I want to know the slope anywhere along the line. I can ask for here, 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 there. At any of these points on the line, I want to know what this is. But a different thing is, at any point on the line, what is the area from the beginning all the way to that? What is this blue area? In this case, it's the stripe. This would be a different case. And this question of what is the area of the curve is called finding the integral. So the slope one is where we get derivatives. So then the question is, what is the slope of the line? Here, we are looking for the derivative. We will also hear the term, we are differentiating. Differentiating the function x, differentiating x. And then the red area part, the area part, is called finding the integral of x. And the process of integration. So you do integration, find the integral. You do differentiation, differentiating, integrating. So you integrate, you perform integration, which is you integrate to find the integral, and you differentiate, which is the process of differentiating, is you differentiate to get the derivative. The derivative will be a new function that is related to x. And that will tell us, that function will tell us at any point x, what was the slope of x. So the derivative of f of x is a new function tells us the slope. And you also hear the tangent line. Now, similarly to the, I said I was explaining what is a tangent line. You heard in geometry, tangent. Remember? Tangent to a circle. Always a tangent to a circle. A line that touches the circle and just quickly, just remember this circle. But previously, we'll make it perfect for you. And the tangent might be and it is the center of the circle. The tangent is at right angles to this radius. The tangent touches the circle only at one point. It doesn't touch, you could zoom in as much as you want. The tangent line will never touch any other point on the circle. Only that one. And there's only one line that can do that. Choose a point on the circle. If you think about it, if I tilt this line a little bit, it's going to touch another point on the circle. So there's only one line that is a tangent. And for every point on the circle, there's another line that is tangent. And you might say, oh, that one looks like it's just one point, but imagine if it's just touches at one point on the circle. So here, what we want in the center is also the tangent to this curve. Every time I put a point here, I want to do a tangent. And the tangent, notice the tangent might cross the line. It still only touches it in one place. Up here, the tangent is like this. Here it's like that. Here it's like this. Here it's like this. Here it's like this. There it is. Alright, so every point on the line has a different tangent. So in a way, what we're asking, we can do these approximations. We can get the average. Here's point 1, here's point 2. So what I want to know is what is the slope of the tangent? And this process of approximating, well, I can get closer and closer to the tangent line. But the tangent line only touches my line, my red line, the curve, at one point. There's only P1. But we know that in order to calculate the slope, I need 2 points. I need a P2. Well, if the tangent doesn't touch the curve anywhere else, what is P2? I don't know. So how do we get a P2? So we're going to take a limit to get around this. So we want to be able to find the slope of these black tangent lines. So the black here are the tangent lines. And the function, the derivative of x, is a function that says, give me any x here along this axis, and you say, if you give me this x, what is the tangent, what is the slope of this tangent? And this new function, the derivative of f, will say, so here, for example, the tangent line here is going down, which means the slope is negative. If something if it slopes downwards, then it has a negative slope because instead of rising, it's falling. So if I run forward from here to here, I actually go down. That's a negative slope. Whereas these are positive slopes. And you can have a slope, if I was right here, there's a slope that is a flat line, which means it has a slope of up. Positive if it's a flat line. So flat line, parallel to the x-axis. The slopes are all constant, and there's a specific number. So think about rise and run. If the line is flat, how much are you rising? You're not rising. There's no rise. Rise is 0. 0 over from distance is 0 divided by a number is what? 0. The slope of the flat line is so the slope of the flat line is 0. If the line is sloped upwards, then that's a positive slope. Actually, the rise is positive. And if the line bends down, then over this line, the rise is negative. So it's negative slope, 0 slope, positive. So the function here, right, here the function f of x is a positive number. But the slope of the tangent is negative. So whatever that function looks like, for the slope of the tangent, it will be a number right down here at this point. So it will be a So here, yeah, this one is an example as well. So in the case of the function, we call this line where we're calculating the average the secant line. So the secant, like in a circle, the secant touches 2 points on the circle. Cuts across. Whereas touches so here. Yeah, we kind of covered this already. So what is the slope of the secant to the function of x? If we have a point A and then another point x, so as x gets closer, we can move x to get closer and closer to A. We have a value of those 2 points, and we can get a slope of the secant that gets closer and closer to what we want is actually the slope at A. But the slope at A is the line that doesn't touch. At least not in the book. So that's the tangent problem. So here we use average velocity and continuous velocity. These are examples of when we want to know if the continuous velocity is tangent. The average velocity we get from the secant. And then, so I was going to get, so the next we said is the area problem. So suppose you want to know the area of your curve. And here's an example. Yeah, so between A and B, if I shade this area, between the x-axis and the function of the x, what is this area? And right now, we're like, why would anyone want to know that? Who wants to know this? Right? Well, we're not sure yet. We will take it from the example. But let's trust that, okay, there must be some good reasons, some good cases, when I want to know the area of the system. But I want to know it in that. For any two values, if I move B and I move A to anywhere, I want to easily be able to get what is the area. But right now, this is very hard to do. Right? You look at this, you know how to calculate the area. So, one way you could imagine, okay, if you have to approximate, you know, well, I don't know but I could get close to the right answer by making little rectangles. I know how to get the area of a rectangle. Rectangles is very easy. Okay? I just take the height and the base, and I multiply them first. So, okay, I can make little rectangles. And I say, okay, this rectangle goes from A to a little bit, and maybe it touches the curve in the middle. And then another one there, and another one there, and so forth. And then I get the area of each of these rectangles, I add them up, and I said that's pretty close to the area